lesson is going to be on analytic systems for very special kinds of systems of differential equations. Completely decoupled and partially decoupled. Those are the special things we're going to learn how to solve today. So number one, partially decoupled, completely decoupled, or not decoupled? Completely, yeah, because the x prime only depends on the x and the y prime only depends on y. So this is completely decoupled. All right, how about number two? Partial, because y prime only depends on y, but x prime depends on both x and y. So this is a partially decoupled. And the last one, not decoupled. Yeah, both x and y depend, x prime and y prime depend on x and y. All right, for a single first order differential equation, chapter 1 developed 3 different analytic techniques for solving it. So what were those for just a single differential equation? Separation of variables. Yep. Lucky guess. And there was one more.
No, it's called where you like the e to the integral.
Yes, it's called integrating factor. By the way, I don't have your quizzes graded yet. You probably figured that out. I'll bring them next class. Okay, so if you have a system of first order differential equations, 2 equations, x and y, the analytic techniques are even fewer and more limited than they are for a single differential equation. But we're going to study some of the methods that do exist because they can offer us insight and intuition that we can use when studying systems for which there are no analytic techniques, where we have to use qualitative or numerical techniques. So first, remember that sometimes finding solutions is really hard, like it's a really long, ugly process sometimes. But once you have a solution candidate, once you're like, okay, I think I solved it, you can always check, right? You can always go take that solution and check, is it really a solution? By taking its derivative, plug into the left, plug into the right, do they equal each other? Just like when you were solving for x back when you first started taking algebra. So it's important because you can check your work, but also many of our techniques are just sophisticated guessing schemes. So that involve making a smart guess and then plugging it back in. All right, so a special kind of system is a decoupled system where one rate of change of one or more of the dependent variables depends only on its own value. So in this case, you can just use techniques from chapter 1, solve each equation separately. Okay, so here's a completely decoupled system with some initial conditions. So has anybody solved enough of these that without doing separation of variables, you know the solution to x prime equals negative 2x? Close. Close. You get x of t is k e to the negative 2t. Yeah. So that's a solution. And then for y prime equals negative y, its solution would be y of t is some other, not necessarily k, some other constant e to the negative t. Yeah. If you haven't solved enough of those by separation of variables to be able to know what the solution is going to be, let's just do one of them by separation of variables for a quick review. Okay. So x prime, that's actually dx dt. Sometimes when I'm typing, it's just way faster to write x prime than dx dt equals negative 2x. Separation of variables says put all your x's on one side and all your t's on the other. And the simpler you can make the left-hand side, the better. So I'm going to leave the negative 2 on the right. So this is just going to be 1 over x dx equals negative 2 dt. So I multiplied both sides by dt, divided both sides by x. Integrate. The integral of 1 over x is ln x. Integral of negative 2 dt is negative 2t plus c. And then to get the x by itself, you raise e to both sides. E to the ln of x is just x. E to the negative 2t plus c is e to the negative 2t times e to the c. This is that little trick about exponents, because when you're multiplying like bases, you would add the exponent. So I'm sort of doing the reverse of the rule, the way we normally use that rule. And so this finally becomes x of t. E to the c is just another arbitrary constant. We'll call it k. K e to the negative 2t. All right, so I'm not going to go through the whole process again for y, but they asked me to solve, this is actually an initial value problem, so I have to find values for k and for c here. So I know that x of 0 is k e to the 0, which is k, and that's supposed to be 1. So they're both going to be 1, yeah. So x of t is going to be e to the negative 2t, 1 e to the negative 2t, and y of t is going to be 1 e to the negative t. So nothing new in terms of technique here. It's just that I had 2 equations to do instead of 1. Okay, so but our next example is going to be partially decoupled. So we're going to get a little bit fancier. All right, so x prime is 2x plus 3y, and y prime is negative 4y. So one of those I can just solve separation of variables, or maybe I just know what the solution is, right? So y of t, I would solve by separation of variables, and maybe you've done that enough times that you know that that's going to come out to k e to the negative 4t. All right, so then you go to your x prime equation, and I'm going to rewrite it as dx dt. And it's 2x plus 3y, but now I know what y is, right? Y is k e to the negative 4t. So instead of putting a y there, I'm going to put k e to the negative 4t. And now this is a linear differential equation, and we can use lucky guess or integrating factor to solve it. I'm going to go with lucky guess. Okay, so lucky guess first says step 1, write down what I'm doing, lucky guess. Step 1 is to solve the associated homogeneous equation, which means just drop the ugly stuff with t, right? So all I have to solve is dx dt equals 2x. And maybe you've done this enough times, you know that the solution will come out to k e to the 2x. So x equals k e to the 2x. And like, because you're finding so many different things in lucky guess, like there's 3 specific pieces, I like to sort of keep track of what I've done by putting a little subscript. It is 2t, thank you. It is 2t, thank you. So I like to put a little subscript h, that means that's the solution to the homogeneous equation, right? It's not my final answer. Okay, so step 2 was to find a particular solution, right? We have to guess. We need to find an x particular that solves the original, right? The non-homogeneous version. So your guess for x particular takes the form of the function of t, the part that you dropped for part 1. It takes that form plus any of its derivatives, right? But when that term is e to the something, you don't have to write down the derivatives because they're all like terms and you can smush them all together. So my x particular is going to have the form alpha e to the negative 4t. So if that's my particular, my guess, I'm going to take this x function, and I'm going to put the dx dt here. I'm going to replace this x with the function, and I'm going to figure out what alpha has to be to force that to be a solution. All right, so dx dt, I'll just write this out, dx dt, yes, is 2x plus 3k e to the 2t. So that's my original dx dt. Now, what is the derivative of alpha e to the negative 4t? Negative 4 alpha e to the negative 4t. So that's what I'm replacing dx dt with. It's the derivative. All right, so then I have 2 times x, which is alpha e to the negative 4t, plus 3k e to the 2t. And I have to choose alpha to make this equation true. Okay, so on the left and the right of this equation, I have an e to the negative 4t term. Their coefficients would have to be the same, right? Because I messed up. What's it supposed to be? Negative 4t. I was looking at the homogeneous solution when I wrote it. Okay, good. That makes this better. Okay, so on the left and the right, all my terms are e to the negative 4t. So I have negative 4 alpha e to the negative 4t, and then 2 alpha plus 3k e to the negative 4t. So the coefficient of e to the negative 4t on the left has to equal the coefficient of e to the negative 4t on the right to force this to be a solution. So I have negative 4 alpha, go up here, negative 4 alpha has to equal 2 alpha plus 3k. And I'm trying to solve for alpha. I'm looking for alpha, so I'm going to, because that was what I started with. I said I need an x particular that looks like this, and I'm going to try to figure out what I have to make alpha to make this work. So I'm going to solve for alpha here. And you end up with alpha equals negative 1/2 k. Just move the, so you have negative 6 alpha equals 3k, divide by negative 6. All right, so that's just the end of step 2, right? I found an x particular, and it's the form alpha e to the negative 4t, where alpha is negative 1/2 k, e to the negative 4t. Okay, so that's an important piece. X sub h was an important piece. And step 3 is just to add those two pieces together, right? Once you have the general solution to the homogeneous equation and a particular solution to the non-homogeneous equation, you add them together, and that's the general solution to the non-homogeneous equation. So x general is x homogeneous plus x particular. So k e to the 2t minus 1/2 k e to the negative 4t. There's my general solution. Oh, those are not necessary. Are they the same k's? Those are not necessarily the same k. Yeah. Okay, so let's see. When I was solving dx dt homogeneous, I wrote a k. We should call this like k2. Now that is the same k. So over here, this should be k2. It's a different k. Sorry. Yeah, I know.
So we're stuck with a system that has two different coefficients then?
Yeah, which is why, look at part B. What did I gave you two initial conditions, one for x and one for y.
I see.
So now you can solve for your k and your k2.
I see.
So you have two pieces of information now. Okay, so x of 0, well, let's write down x of t is x general. That's k2 e to the 2t minus 1/2 k e to the negative 4t. Okay, so it told me that x of 0, when I plug 0 in here, I should get k2 minus 1/2 k, and that's supposed to be 0. So that's only one equation. I still have two unknowns, so I can't solve it yet. But y of 0, I have a solution y of t that I came up with in the first like 5 seconds of starting this problem. It was k e to the negative 4t. Yeah, I used k, right? Yeah. So then y of 0 is k, which in this case they told me is 1. So I now know k is 1, so I can go over here and solve for k2. So k2 is 1/2. And then your solution to a system has to be two functions where you replace the k and the k2 with these numbers. Okay, so y of t, let's write x of t first. X of t is k2, 1/2 e to the 2t, minus 1/2 times k, so that's 1/2 times 1 e to the negative 4t. So there's my function x of t. And y of t is k e to the negative 4t, and k is 1, so it's e to the negative 4t. So I have a solution for both x and y.